moi. Attends, Asma. Non, mais il faut dire aux gens.
Ça sera à mettre.
En fait, c'est pour que les gens entendent en ligne.
Oui. Ah oui, d'accord.
Non, si t'as pas ça, ils n'entendent rien. Et après, tu dois le passer aux autres, sinon ils n'entendent pas les questions ni les réponses.
On n'a pas ça, le film.
Ah, moi, je l'ai acheté.
Elle est juste صفقة هي قاعدة غادي.
هاي مريم حاضر ما هو مريم شكون معك اقول لهم من واحد يقول لهم راهو عندنا اللي ما عرفش نقول له ما ياكلوش برشا فلوس فطور
Is it working?
No, they are
Yes. Can you hear me?
if you are here you don't know in which they're connecting so they are using that you are all time late so they are getting a little bit late.
That's the Tunisian way of doing things, right?
Yeah. They are connected.
Test. Okay. Can you hear me? Can you hear me? Yeah. Okay. Thank you. Test. Can you hear me? Ah, okay, great. Yeah, I know. Vous êtes en train de partager votre écran. Nous avons 2 participants. Comment ça va? Can you hear me? Test.
Yes. If you want to check the microphones.
All right, sir. Can you hear me? Should I start? Or? Well, welcome everyone to the morning session. And today's first speaker is Emmanuel Lepinette from the Paris Dauphine University. And he will speak on dynamic programming principle and computable prices in financial market models with transaction costs.
Okay, thank you. Maybe I have no?
Like this. That should probably work.
Okay, so thank you. Hello everybody. So first, of course, thank you to the organizers for this nice conference. Actually, this is like a dream for me because it was one of my dreams to see an oasis for the first time and the desert as well. So, thank you so much. Maybe I am a singular person in this conference because we are not a lot to work in the field of mathematical finance in this conference. But I hope to convince you that mathematical finance is not only finance, but also mathematics, not statistics, no more, but mathematics. Actually, I hope also to convince you that finance is inspiring for mathematics, actually. There were a lot of interesting problems, and some of them are related to orders, actually, random orders. This is the way we started the discussion a very long time ago with Amin. That is from this that we had the opportunity to know each other better, and now a priori we are friends. I hope so. A priori, yes, because I am here. So thank you so much. Okay, how does this work? So like this. I have just to put on, maybe. No? Oh, it's okay? Okay, I just, okay. So I'm gonna take time to explain this. Okay, so not work. Oh, that does not work. Maybe like this. It's okay now? Okay, don't worry. So, okay, so I'm going to present a problem, a very classical problem, which is called the problem of hedging, or sometimes super hedging European claim. So this is motivated by finance. So in this talk, I'm going to consider discrete time. Okay, you know that in finance, time is very important in general. So you do not solve the problem in static way. So we consider discrete time to simplify T0, 1, 2, etc. And a financial market model is mainly defined by a few concepts. Precisely, we consider a discrete time complete stochastic basis. What is it? We consider omega, like in the theory of probability measure. Omega is interpreted in finance as a set of all possible states of your financial market. So all that should happen in the future, say between 0 and some horizon debt capital T. Okay, and then you consider what we call a filtration FT. This is a family of increasing sigma algebras, and at time t you interpret ft as information available on the market. That is what you see from the financial market. Okay, and at least as usual a probability measure p. Okay, now we consider f capital T measurable, that is only observable at time capital T, a random variable I call psi t, that we interpret as the payoff of some European option. What is a European option? This is a contract delivering the terminal wealth psi t at time capital T. Means that, okay, you can buy this contract at some price you give at time 0, and in exchange you're gonna receive from the seller the terminal wealth psi t. In general, this terminal wealth is random and is a function of so-called underlying asset, that is a function of some risky asset price. For instance, imagine Airbus in France, Airbus stocks. You can buy Airbus stocks, shares, etc. And an option on this underlying Airbus price is a function of this price. So that means that, of course, you don't know in advance. If you buy such a contract, you don't know in advance what you will receive at the end. Okay, for the for the seller of this option, the difficulty is that you have this obligation to deliver the swaps, but you do not know in advance what you will deliver at the end. Okay, so how to do it? You ask the buyer some money at time zero, and with this money, you try to construct an investment whose terminal value is larger than the wealth you have to give to your buyer. Okay, so that's simple a priori, but of course the problem is how to invest the initial money you receive from the buyer to at the end get a terminal capital which is larger than the payoff. Okay, so a priori this is not so trivial. Okay, because all is random, of course. So this is what I wrote here. Solve the following: find a portfolio process, so investment, okay, whose value evolves in time, of course, a priori is better, such that terminal value is greater than to the payoff. If equal, we say hedging or replication, or otherwise greater than super hedging. Is a detail but very important for us. Okay, so actually I wrote find a self-financing portfolio process. So what means self-financing is that actually you construct this portfolio only from the initial value, initial capital. The initial capital you have is the money the buyer gives you at time zero. Okay, that means that you don't intend to consume a part of the investment you construct to reach the payoff, and also you do not need your own money, okay, to this portfolio, of course. You just use the money given by the buyer to reach your goal, okay, so that you can deliver the terminal wealth society. This is a general problem, very classical in finance and very interesting, actually. Sorry, I think it's okay. Now, I'm going to present different models. First, models without transaction cost, and then with transaction cost. First, the market is composed of different assets. The first one is generally asset number one is what we call a bond. That is mainly what you understand is cash, okay? Because you use cash also. And so without generality, we suppose at any moment cash, the price of 1 unit of cash is one like 1 dinar, 1 euro, $1, and there is no interest rate. That is, interest rate is zero. That is when you have a cash deposit, then 1 euro today or 1 dinar today is still 1 dinar in 1 month, for instance. Of course, you may imagine other hypotheses, but you can just rescale the prices dividing by the first asset, so that it is always one. So this is without lots of generality. So imagine first price corresponding to cash. Okay, the other assets are risky in the sense that they are uncertain in the future. You don't know by even their prices, of course, and that corresponds to as I told you, Airbus shares, BNP for France, I don't, okay, or the same in Tunisia, okay? And now, what is a financial strategy? It is just the quantity of assets you decide to have in your investment, just that. So very simply, okay? So this is what we call a financial strategy. So this is a vector valued stochastic process. Why a stochastic process? Because at any time, the quantities of assets you have in your investment is at time t ft measurable in the sense that depends on the information you have at time t. At any time t, you can change the composition of your portfolio, and you change it in terms of what you observe in the market. Okay, this is natural. Okay, so now let us see first What happens without transaction cost? Without transaction cost, what we call naturally the liquidation value, that is a value in cash of your investment. If you liquidate everything, that is you sell your risky position, your shares, what is the cash you get, the sum of the quantities multiplied by the prices, just that. This is very natural. This is what we call the liquidation value. Actually, this is simple here because we do not have any transaction costs. I'm going to explain why this is so simple in that case. Now, what is the self-financing condition we impose on the portfolio processes in discrete time? This is the following. At time t-1, theta t-1 multiplied by the price at time t equals the quantity you have at time t multiplied by st. What is the meaning of this? Imagine you have chosen the quantities you want in your portfolio process, theta t-1 at time t-1, okay? Now it's sin t. What is the liquidation value? Quantities you have multiplied by the new prices at time t, okay? After you change the composition of your portfolio, that is you change theta t-1 into theta t. What is now the liquidation value? This is the new quantities multiplied by the same price at time t. Okay, why this equality? This means that before changing and after changing the composition of your portfolio, you have the same value. So there is no loss. So no loss when you make some transactions, because if you want to change the compositions of your portfolio, this means that you certainly have to buy some other, some quantities and maybe sell other ones to change the quantities, right? And a priori, when you buy or sell some assets, you don't have transaction cost. This is why it is possible in that case to suppose that the self-financing condition is this one. No change in the value. Okay, so of course there is no consumption of money and there is no, you do not add money to your portfolio. Equivalently, you deduce that the liquidation value satisfies the following dynamics. The variation between two dates of the liquidation value is given by theta t-1 delta st. This is very simple to understand. This means that from time to time, what you get as a profit or a loss is just the quantity of assets you have multiplied by the variations of your price. Imagine that you have bought 10 stocks and from between yesterday and today, the price goes up to 5 euros. Then your profit is 10 multiplied by 5, just. Okay, so it's very simple. So this, what is interesting is that from this, you have now an expression of your liquidation value as LT is the sum of its variation. That is the sum of theta t-1 delta st, a telescopic sum, you know. And you can interpret this like a stochastic integral or integral if you prefer. That is LT is L0 plus the sum of the variation, right? U between 1 and t, and it's just L0 plus the sum between 1 and t of theta u minus 1 delta su, and this is a kind of integral, right? As you know, Riemann sum. This is a random one, of course, and now imagine what happens in continuous time. You have limits and you get this famous notion of stochastic integrals. So this is interesting for mathematics. Okay, so where is my, no. Okay, now let's go. So yes, I am a mathematician, so it's not surprising. Okay, so now let us see the corresponding model, but with transaction cost. With transaction cost, now it's not possible anymore to model an investment as the liquidation value of your positions. So we directly work with the quantities you have. Mainly for me, so just to simplify, without transaction cost, for me, a portfolio process is a location value, so real value process. With transaction cost, I don't have any choice but defining a portfolio process as a vector valued stochastic process, that is the quantity of assets you have. When I say stochastic process, I mean that at any time, the value of your investment is FT measurable. Okay, so the function of the information you have at time t. So in that case, the liquidation value of your positions is not always simple to express. Actually, it is generally very difficult, actually. So how to define a market with transaction cost? We introduce a set valued stochastic process, that is a random variable GT, whose values depends on omega, so random variables, but this is a subset of RD, a random subset of RD. The subset of all vectors, that is vectors of quantities, so financial positions, whose liquidation value is non-negative, with what we call solvent positions. That is, if you have such a financial position, okay, you can liquidate and get the cash, and the cash is non-negative. So that's perfect. Okay, you are without any debt. Okay, so of course we have to impose on LT some technical conditions, in particular at time t, LT of any financial position is FT measurable. That is, at time t, with the information you have in the market, you are able to compute and to know how much cash you have in your investment, because you observe the prices, for instance. And for technical conditions, we generally suppose that the mapping X maps the liquidation value of X for some omega is upper subunit continuous. Okay, technical conditions. Under these conditions, we may show that GT is a closed almost surely. Okay, is closed, unmeasurable, so means observable at time t. Okay, and the measurability should be understood as follows. That is a graph of GT, a set of all pairs of omega X omega in capital omega, X in RD, so that X belongs to GT of omega, belongs to the product of the sigma GR FT multiplied by BRD. About the intuition means that at time t, you are able to observe the value of your solvency set from the information you have. Okay, you are able to identify the vector valued financial positions whose liquidation value is non-negative. Okay, so perfect. Now, equivalently, so I told you I explained to you that we may define this solvency set from the liquidation value process, but reciprocally, if I give you a priori an arbitrary closed random set GT, I can recover the liquidation value as follows: a supremum, but actually a maximum under some conditions on GT, so that you interpret LT of Z. Z is a vector of quantities. LT of Z at time t is the largest amount of cash you can get when you liquidate your position Z as follows. That is, you change Z in alpha 1. What is alpha 1? This is a vector of quantities, that is alpha 0, 0, 0, means that you have the amount alpha of cash and 0 risky positions here. So yes, I was saying that LT is, so you can change Z in cash, that is this position. Why? Because you can just write Z as Z minus alpha 1 plus alpha 1. And it's possible to get rid of this position because you impose this position to be in GT, meaning that the liquidation value of this is non-negative. So you swap money maybe, but you are not in debt. So it's possible to change Z in cash. And this is the maximal amount of cash you can get from your financial position. Okay. So also there is another concept related to the liquidation value. If you define the random function CT of Z as this, then you interpret CT of Z as a cost. Precisely the smallest cost for me is cash. The smallest amount of cash you need to obtain the financial position Z. Okay, Z, I recall, Z1, Z2, etc., is a vector of quantities you want in different assets. So the cost function for any position Z is the minimal amount of cash you need to have this position Z invested in the different assets S1, S2, etc., accordingly to the quantities Z1, Z2, etc. Okay, and what I have maybe to precise also is that in our model we do not impose any restrictions about the quantities Z1, Z2, etc. So they can be in particular negative. Okay, so you can borrow money in cash. So Z1 is negative, but also you can borrow risky positions. That is Z2 may be negative. You're not obliged to have positive quantities of risky assets. So we talk about short and long positions, short position for negative quantities. Okay, this is possible in practice actually for professionals in banking system. Okay, so so now what we have to observe is that the cost function a priori, of course, depends on the available quantities and prices for the risky asset. So the cost function of any position Z at time t depends on the prices ST, maybe the available quantities. So this is why this is a random function. Okay, so that should depend on what you're gonna see in the future at time t. So this is also FT measurable. So in general, ST maybe a vector value process whose dimension is larger than the number of assets. Because many parameters are a priori needed to express this cost function. We're gonna see an example after. So for technical reasons, we generally impose some conditions on the cost function, in particular very natural ones like this one. The cost to get zero position is of course zero. Okay, but this one is due to the fact that X is a vector of quantities. You add some cash and you want to buy this position with cash, then just buy this position X and add the cash corresponding to this position. Don't mind if you don't understand very well this, but these technical conditions which are observed in practice, this one is very easy to understand. If you have two vector of quantities such that x2 minus x1 is an R plus, the natural order on RD plus. That means that in x2 you have more assets than in x1, so the cost is larger. Okay, so something simple like this. Now, what is a self-financing condition with transaction costs? This is interesting for you, actually, this dynamics. The self-financing condition is the following: delta VT. Remember that here VT is the value of your investment at type T, and it is defined as a vector of quantities you have. Okay, so VT belongs to RD plus for us. So delta VT, VT minus VT minus 1 belongs to minus GT. GT is a random set. Okay, why? What is intuition behind this? Imagine you have chosen the quantities of assets you have at time t minus 1, that is VT minus 1. Now you are at time t, and you want to change the quantities VT minus 1 into VT. Just write VT minus 1 as VT plus this residual term that is VT minus 1 minus VT. Okay, very simple. Now, if you want to change this into this, you have to get rid of this residual term. How to get rid of this? One of the possibility is you buy the position delta VT at some cost. Once you have delta VT, you add to this so that you cancel this term. You cancel this term, right? So actually, you don't want to add money to this because self-financing means you just play with the initial value V0, that is the money the buyer of the option gave you at time 0. So if because you don't want to add the money, the cost should be negative, 0 or maybe negative, okay? So that means that you can buy the position delta VT for free, for nothing. So that once added to this term disappears. And then you have changed VT minus 1 into VT. Equivalently, we could say that the liquidation value of this is non-negative because the liquidation value is minus this, okay? So, and meaning that we can also say that to change VT minus 1 into VT, you get rid of this because you can sell this position and you get the liquidation value non-negative, so without any debt. Okay, so two approaches which are equivalent. This is our self-financing condition. Maybe just a comment about this. This you in the maybe I avoid this. No, we in the models with proportional transaction cost. That means the transaction cost you pay when you change change the composition of your portfolio into a new one, selling or buying some quantities of asset, is proportional to the amount of assets you buy or sell. Okay, so linear problem. In that case, GT is a random closed cone, a positive cone precisely. That is a cone which is both convex and positively homogeneous. So this means that in that case, we have a random preorder, the famous classical random preorders, which is x greater than y if and only if x minus 1 belongs to GT, right? So this means that for you, a self-financing portfolio process is just a decreasing process with respect to the corresponding stochastic preorders. Okay, I remember several years ago, I worked on this random preorders, and we have published some papers in this direction. So this is very interesting, actually, and the corresponding stochastic preorders are generally characterized by measurable multi-utility representations. Maybe you know this kind of thing, I guess so. And because actually in the conic case, GT is characterized by its positive dual cones. And so we may have countable representations of this, and then we get a dual representation actually of the random order. So many interesting things for you if you want to add the probabilistic structures to your maybe research spaces, orders, etc., etc. So this is what I would like to emphasize. Okay, so now an example, a classical example of models with transaction cost is the famous, what we observe in practice is that the financial market is generally defined by an order book. Precisely, when you want to buy or sell some risky assets, and you have to face some prices and some corresponding available quantities. Mainly if you want to buy 1 unit of asset, then you're gonna face what we call an ask price. Okay, but immediately after having bought 1 unit, okay, imagine that now you want to sell it immediately. Don't expect to sell it for the price you have bought this unit of asset, but a lower price, bid price. This is also what you observe for the currencies. if you want to exchange euros in dinar, etc., you have two prices, a bid and ask prices. The one when you buy one unit, the one when you sell. And the bid price, that is the one you get when you sell, is smaller than the one when you buy. And the difference is what we call spread, but also that corresponds to some transaction costs. Okay, for risky assets, this is the same, but in generally, okay, if you want to have the smallest price when you buy, then you just have a limited quantity of assets proposed at this price. So if you want to buy more assets, then you have to reach the lines of your order books, and so to accept to have a higher price. Okay, so this is why there are different lines when you want to, with different price, different bid prices with some quantities when you want to sell, and the same when you want to buy. Okay, in that case, what is the cost function corresponding to this situation? This is rather complicated. Actually, the cost function of your vector value quantities is the cash you want, because the first position is cash for us, plus the cost to have each of the components, that is the quantities you want. Okay, so now the question is, what is the cost to get, say, xj units of asset number j? Actually, the cost function are of this form, so rather complicated, but don't mind. What is important to see is that if you want to buy or sell some quantity y, then that depends, of course, at time t of the bid or ask prices you face at time t. So clearly, this is random. Okay, and FT measurable because S ask and S bid prices and quantities as well are observable at time t. So depends on the information you have about these observations. Okay, this is what we have to understand. Now let us go to the superhedging problem I want to expose to you today. Without transaction cost, this is a very classical problem with the literature. How the mathematicians solve it? Actually, they make an assumption, the so-called non-arbitrage condition, which is in economy a market equilibrium. A priori, whether fictive, some practitioners say that it is not realistic, but mathematicians like this because thanks to this condition, they can solve the problem. And so, of course, they're going to say, okay, that's natural. So they like to motivate it by financial reality. But in practice, this is like whether hypocrite. They just use this because by this way you can solve the problem. Okay, of course. But what is this condition? If you have a self-financing portfolio process starting from zero, okay, it's possible to start from zero because you can borrow money. Okay, then if you have chance and the terminal value is non-negative, you start from nothing, and at the end, the liquidation value is non-negative emotionally. You are very lucky because you don't take any risk. From zero, you start from zero. At the end, you do not have any loss. In that case, don't expect to make a positive profit under NA. That is necessarily the liquidation value is zero. In other words, there is no what we call arbitrage opportunity, and an arbitrage opportunity is a possibility on the market to start from nothing and at the end to have a terminal value which is non-negative, but moreover, there is a chance, a strictly positive probability for LT terminal value to be strictly positive. Don't expect to see this in the market. And the economic intuition is that if there is such arbitrage opportunity, certainly the agents acting on the market, being very well informed thanks to the information FT, should detect this arbitrage opportunity, and immediately all of them should try to utilize this. And so because of that, you should influence the prices, impact the prices so that this arbitrage opportunity disappears immediately. This is the explanation, okay? So under this condition, what is very nice in mathematics is that there is this DeLong-Morton-Willinger theorem from 1990 saying that, okay, this NA condition is equivalent to a resistance of what we call a risk-neutral probability measure. That is a probability measure equivalent to the initial one, under which the price process S is a Q martingale. Wow, that's very nice. Actually, there are equivalent characterizations in continuous time. Okay, and so actually, this theorem is just based on the famous Hahn-Banach separation theorem. Okay, so you can see these risk-neutral probability measures as dual elements if you think of their density, Radon-Nikodym theorem, with respect to P. The densities of these risk-neutral probability measures are the dual elements to separate two sets. Okay, what is interesting for mathematicians is once you have done this, then now we are able to find the minimal initial value of the self-financing portfolio process whose terminal value super edge your payoff. This is our initial problem. Recall, our problem is to find an initial amount of money at time zero you ask to the option buyer. Okay, so that's starting from this initial capital. We can start a portfolio process whose terminal value is greater than the payoff. Question: what is the minimal amount of money you have to ask? What is the minimal amount value of your portfolio process whose terminal value is greater than XIT? The answer is given by this formula. At time zero, you should ask the option buyer this quantity, supremum of the expectation under Q of your payoff XIT over all risk-neutral probability measures under which the price process is a martingale. Okay, this is the minimum amount. Okay, of course, if there is only one risk-neutral probability measure, in that case, there is no supremum. In that case, we may show that actually this is replication. That is, at the end, VT precisely equals the payoff. But in practice, this is very difficult to compute this quantity, as you can imagine, because this is a supremum first, and in general, how to identify all the set of possible risk-neutral probability measures. So how to use this? In practice, we just choose a model, a nice model, and actually for which the price process is a martingale under some fictive probability measures. Okay, generally a parameterized one, like the Black-Scholes models or other ones. And then now we try to fit this theoretical model to what you observe in practice. And then once it is calibrated, we can try to play with this. Okay, but of course, because of this, there is an error of model. Okay, so, okay, this is what we can do. Now, okay, what's this? Okay, so sorry. Now, the problem with proportional transaction cost is more difficult, of course. So, in the literature, the first papers in that direction were recent, but the idea is the same. Try to find some non-arbitrage conditions to have dual elements so that we have the same result. Actually, it is only possible for proportional transaction cost because we need to use the Hahn-Banach separation theorem. And so once again, we need to have a conic model, actually. A convex model is not enough, actually. We need to have a conic model. And so there is this famous so-called NAR condition. Don't mind about it, it is interpreted as NA. But under this, we can prove that this NA condition is equivalent once again to some dual elements, which are here called strictly consistent price systems, that is martingales, which is very funny, martingales, whose values belong to the positive dual of the solvency cone. Here, with proportional transaction cost, we have random positive cones, random cones. Okay, so the dual elements that appear when you apply the Ad-Banach separation theorems are martingales evolving in the positive dual of the solvency cone GT. Okay, and if you have such elements, then it's possible to characterize as well the minimal capitals you need to start a portfolio process with terminal value is larger than the payoff as follows, very close to what you saw before. That is a supremum of all these martingales of expectation of ZT, XIT. Here, imagine with respect to the last formula, it is like a density, okay, but vector value here, okay? Okay, so now, of course, this is still difficult to compute because how to identify in particular the set of all consistent price systems. So, but worse, in general, the transaction costs are not necessarily linear. Okay, generally they are at least convex and sometimes not convex if you have some fixed cost as it is usual to observe. So very difficult to compute in practice. This is why I propose a new method here. That is, I propose to solve directly with backward dynamic programming principle the problem. The problem I suppose to use the following: find a portfolio process V whose terminal value is greater than XIT. But so, okay, and because of the self-financing condition, you should solve VT-1 greater than GT, the random preorder, with respect to VT. Actually, here, this relation is equivalently characterized by liquidation value is non-negative. But we have a chance because the liquidation value of any vector position is mainly the cash plus the liquidation value of the risky assets. So you can, in some ways, transform the problem into a scalar one, just in terms of the cash. This is what we do, okay, because of this. And then finally, solving the problem at time t-1 is mainly solving the problem of how much cash you have to have in your first position, okay? And you get this a priori, okay? Not important to understand the details, but what is important is actually to see that this random variable is ft-1 measurable, and this one f capital T measurable, so there is a gap of measurability. And so the most important concept we need here is the operator essential supremum knowing ft-1. What's this? This is a measurable supremum. Okay, and indeed, by definition, the essential supremum knowing ft-1 is the smallest ft-1 measurable random variable that dominates this f capital T measurable random variable. Okay, so we can compute some things, and once you have done this, okay, finally we are able to characterize the value of your portfolio at time t-1. So after you can repeat. Okay, this is the main idea. The difficulty for us is that we'd like to compute this famous essential supremum ft-1. This essential supremum ft-1 is very interesting for you. This is an operator. Like the conditional expectation is an operator, it shares some common properties like the tower property you like, certainly, for the conditional expectation, even in risk spaces, I guess. So it shares this property. It also shares this property of projection. Okay, you know that the expectation of X knowing H is X is H measurable. Okay, this famous projection. This is the same for essential supremum. And there is a dual concept, which is the essential infimum, of course. And okay, so I think this is interesting for you. So once it's done, once this is done, you can compute some things. And actually, at any time, we are able to say that the minimal self-financing portfolio process allowing us to get the payoff at the end, okay, the strategic problem is characterized through such an essential supremum and through the strategy you choose. The strategy you choose from time to time is to change the last position into the new one, involving some cost. Okay, just to understand this, of course, it's not possible to understand everything in just a few minutes. But once you have done this, actually, the very question for us is how to compute the smallest portfolio process, super hedging the payoff. This is a value, a candidate to super hedge the payoff at debt terminal t. And so here, essential infimum means that we want to minimize. Okay, minimizing random variables is not so simple, because minimizing at time t means that you have to find the smallest random variable. And this, you know that if you have an arbitrarily chosen family of random variables, then the infimum of such family is not necessarily a random variable anymore. You know this. So this is why there is this concept of essential infimum. That is the largest random variable, which is smaller than. Okay. So this is a measurable infimum. This is a measurable supremum. And for us, the difficulty was how to compute that. Okay, this is our difficulty. Here, okay, dynamic problem principle, because the idea is that we have proved that it's possible to compute from steps to step backwardly our portfolio processes. That is, given that you are able to compute something at time t plus 1, then you deduce what happens at time t, etc., etc. Okay, so don't mind about that. What is important is maybe the following: how to compute an essential supremum. Okay, imagine that capital X is a random variable, which is f capital T measurable, it's only observable at time terminal debt. Okay, now you are at time t, you want to compute the essential supremum of a function of x. It appears that we have shown that under some technical condition, an essential supremum is just a pointwise supremum. What I mean pointwise supremum, I mean deterministic supremum. Okay, but omega wise. That is, for each omega of your space capital omega, the essential supremum may be computed at just a supremum of your random function over the conditional support of x. The conditional support of x is what you know in general for the trivial sigma algebra. You know the support of a random variable. This is a range of all possible values, okay, deterministic one. Here, this is the same notion, but updated to time t with more information. At time t, you have some information. So the support of x is the smallest closed random set ft measurable, okay, under which x lies, okay, the ft measurable range of possible values. Okay, so finally, it's interesting because we can compute this omega wise. Okay, and this is new in this theory, because actually there is another lemma equivalent for the essential infimum, which is actually formulated in Rockefeller. No, excuse me, I'm not crazy. Yes. Rockefeller books, and actually for the essential infimum there is no problem. Okay, this is something which is known. That is also an essential infimum may be computed as an infimum over the random set. This is very important for us because now we have a recipe to compute numerically the things. This is the novelty actually, and once it's done, I think it's okay for today, because I have many things to say. What is my conclusion? Is that because of these new techniques, it's now possible to compute backwardly the infimum super hedging prices of a given payoff. Okay, backwardly, thanks to this operator's essential supremum and essential infimum, which are finally just pointwise supremum and infimum over random sets. Okay. Actually, okay. And what I would like to say is that I hope that this work will inspire you, because there are some very interesting, I think, concepts like random operators. Okay, essential supremum, essential infimum. Also random orders, so which are very interesting. I had the opportunity to work on it, and indeed our problems are not the same than yours. In general, you suppose that any family of points admits a maximum and infimum, but for us that's not so trivial. Okay, that's not so trivial, because of course we impose some measurability in particular. So this is what I want to say for today. Okay, thank you.
For the talk, are there any questions or comments?
Excuse me, yes.
Thank you very much for the talk. I was wondering, these transaction costs act essentially as regularization. So they penalize the temporal derivative of your strategy, right? So you're not, if you buy and sell and buy and sell and buy and sell and buy and sell, the derivative of each asset is very high, right?
Initially, the transaction costs are introduced because we observe transaction costs in the real market. Because this is not just to play with mathematics, because it is motivated by real facts. Okay, so of course the problem is completely different if you have a transaction cost, because it's you can exchange actually any asset to another ones. So the process to change last position VT-1 into V is not simple. So it's not possible to scalarize the problem. I don't know if by this way I answer your question, because I'm not sure about your question.
So I understand that the transaction costs arise naturally, but if you think of a decision maker who comes up with a strategy, because every action costs something, they will only take this action if it's worth it. So their strategy will be sort of naturally penalized by the way the market is built. The derivative of that strategy will be penalized just because it's expensive to do things.
Yes. Once you have accepted, once you have accepted to sell an option, you don't have any choice but investing, so that at the end you get a portfolio with terminal value is greater than the payoff. So you are obliged to make a transaction. And clearly, if you just keep V0, you have no chance to get at the end psi t at least, because V0 a priori is not greater than psi t. So you are obliged to pay some transaction cost. And so, of course, the question is to minimize the transaction cost. And this is why here what I try to explain is to find the smallest portfolio process whose terminal value is greater. And so we are seeking for a minimal element indeed. And in that direction some time ago, yes, I remember having published some papers in that direction. That is a problem of finding a minimal element with respect to some random preorders. The problem is that you don't have just one random preorder, but a stochastic family of random preorders. So you have to minimize actually from step to step. And this is why that naturally appears dynamic programming pretty simple. That is, you first minimize VT-1 and then VT-2, etc., etc. I hope that. Yes, sure. You can.
So where I was trying to get to with this question is, I could think about it because it's easier for me as a variational problem. So you optimize over the whole strategy so that your final payoff is as large as possible, and your strategy is somehow constrained or penalized by the transaction costs. Is that a valid way of thinking about it?
Yes, yes, actually, and but don't confuse. There is another problem which is different. Okay, there is. We have to be careful. Here is a very particular area because we want to hedge something. Because the other problem is to maximize your terminal waste. Another problem. In that case, you start from a given initial capital, you construct a strategy, and your goal is to have at the end the largest wealth you can for a given control risk. This is another problem. In that case, the idea, such a problem exists as well. That is an optimization problem, and in general, we solve it through utility function we fix, okay, which a priori models your test with respect to the risk. Okay, this is another problem. Okay, okay.
Other questions or comments? Oh,
Thank you for this talk. I have a question. You are looking for infimum and supremum and to look at prices, so you can do any strategy you want, but you didn't care about all the Greeks in markets. So Greek, alpha, beta, that must be neutral. So you are not working like this in reality.
Sorry, actually, these famous Greeks appear naturally when you start from the Black-Scholes models, right? And actually, after that, sometimes they like to use these Greeks like indicators. But if you actually, you know that Black-Scholes model is very used, but in practice not realistic. So there is clearly a significant error of model when you use it. So using the Greeks like indicator is rather artificial and just inspired by the Black-Scholes model. So actually here, okay, if you are using the delta hedging models, that cannot work except if first your data follows the Black-Scholes models, and moreover, if you have very large quantities of debts, so that the step different debts goes to zero. Otherwise, you cannot expect this method to work.
Yes, it's a risk control. So what I said, it's like risk appetite. So after 2008, we imposed to the market to have like neutral at the end of the day, they have the neutral Greeks. That means that alpha, beta must be as close as possible to zero.
This is not the same problem. This is when you start from a and then you just want to increase your wealth. Here we just want to reach target. This is not the same problem. You do not have any choice but reaching your target, because this is your obligation with respect to the buyer of the option. So here, you just have to be sure that the terminal value of your portfolio is larger than the payoff, almost surely with probability 1. Sometimes we may relax this condition by imposing only that the terminal value is greater than XIT, say in 95% of the cases. And so in that case, think of the so-called risk measure, value at risk, etc. In that case, okay, you can relate this to the choice of some constraint of risk. Yes.
Due to time constraints, I propose that any further questions are delayed until the next break. And in the meantime, please stand by while we set up for the next speaker.